What's up, skeptics? Welcome to another episode of Reason to Doubt, your source for all things skeptical. I'm your host, Jordan. Jared isn't with me today. He's feeling a little under the weather, but I won't be flying completely solo. I've got a very special guest. We are going to be talking about the multiverse, whether or not it exists, why we might think it exists, and how that would impact the conversation of whether God exists. Before I dive into that, I've got a fallacy for you. The fallacy of the day is the no true Scotsman fallacy. It's also known as like the purity test fallacy. Basically, you make a generalization, you paint with that broad brush, somebody gives you a counterexample, and you say, well, that doesn't count. No true X would believe that. So the classic example is Angus, being a Scotsman, says that no Scotsman would put sugar in their porridge. William says, well, I'm a Scotsman and I put sugar in my porridge, to which Angus says, well, no true Scotsman would put sugar in their porridge, so you're not a true Scotsman. So you don't count. My generalization stands. You can do this with any kind of group. You could say that no true Christian would support abortion rights, or no true liberal would endorse gun control, or whatever you want to do. There can be good reasons, though, to exclude someone from a group, just kind of definitionally. So if somebody was claiming to be a vegetarian, for example, but they eat meat all the time, then you could rightly question whether or not they are actually a vegetarian, since not eating meat is literally the definition of being a vegetarian. So you can use that, and that's not necessarily fallacious, but just maybe put those broad brushes away. They tend to get people in trouble. So with that out of the way, we're going to get into our conversation. Before I dive into this, I do want to apologize. I have recently rebuilt my computer, and my audio switched from this really cool mic I have here to the potato webcam that I have recording me. So it sounds like I'm yelling at you from across a vast distance, and I apologize for that. But unfortunately, I can't go back in time. But in some version of the multiverse, I did use the right microphone. So if you happen to be in that branch of the multiverse, then you're going to have a much better listening experience. Anyway, the person joining me today is Dr. Jeff Zweerink. Jeff is from the Reasons to Believe group, and he's an astrophysicist. He's a research scholar for Reasons to Believe. He earned a PhD in astrophysics from Iowa State University. His writing focuses on encouraging people to consider the connections between the truth of Scripture and scientific evidence, kind of putting those two together. He's the author of Escaping the Beginning and Who's Afraid of the Multiverse, both books I have and have read, and they're great, highly recommended, and also the co-author of the Impact Events Student Devotional Series. So thanks for joining us, and here's the conversation I had with Jeff.
Thanks for coming on, Jeff. Really appreciate you taking the time to come chat with this humble engineer.
Well, I'm looking forward to our time here, Jordan. Love talking about the multiverse and enjoy interacting with you.
Yeah, I'm a bit of a physics nerd, so this is super exciting for me. Today, like I said, we're going to be talking about the multiverse and probably get into what it is, why scientists think it might be a thing, and what, if any, implications it could have on the conversation surrounding God and theology. I picked up your book. I read it over the weekend. I was camping with my daughter, Who's Afraid of the Multiverse, which I swear he doesn't pay me to pitch these books. I just read them because I think it's interesting. But before we get into the meat of the conversation, probably not everybody reads cosmology books in their free time. So could you briefly go over what is the multiverse and why do people think it might be a thing?
So the way I describe it typically is, if you're going to talk about a multiverse, which is many things, you got to talk about what the universe is. And there's no arbitrary, uniform, agreed on, set upon definition of that. But the way I like to think about it is that in our universe, there's the speed of light has a constant value. It's a finite and constant value, which means that the further away you are, the longer it takes light to travel to us. We live in a universe that's about 14 billion years old, and it's expanding. And you put all those three things together, and what that means is that there is a most distant reach where anything has the possibility of transmitting from that location to the Earth. And so I just define that as a universe, or it's more generally talked about an observable universe, Hubble volume, lots of terms for it. But it's just the idea that this is the most distant region of space where we can actually interact with it in some way. And now, granted, this is a very large region. It's about roughly 50 billion light years in radius, and it's centered on the Earth because that's where we defined it to be centered. That's not saying the Earth has any special location. But so if we can decide or define that as the universe, then the multiverse really is just anything beyond that. And that might seem ludicrous or weird to be talking about that in a scientific context, but there are, this idea of inflation that's out there. Well, part of how inflation explains some of the observations we see in our universe is that there's a very rapid period of expansion, and that means that the universe is much larger than what we can see. And when you're so really, the multiverse is just anything beyond the region of space-time that we can see. Now, you get beyond that, and there's different ways to think about what could be beyond. It could be just a whole lot more of the same stuff. It could be entire other realms where the laws of physics look different. You can get quantum mechanical multiverses. You can get mathematical multiverses. So there's a lot of diversity once you get into, here's a multiverse. But really, just the multiverse is anything that is beyond the physical realm that we can see.
And you said, obviously the universe is thought to be about our observable universe, our little region of space, is thought to be about 14 billion years old, but the size of it is about 50 billion years old. The part we can observe, right? So how does that work? The fact that it's only been around for 14 billion, but it's bigger than that.
Well, what accounts for that fact is that the universe is expanding. And so what happens is, if we were to take something now and say, all right, there's some distant location which starts emitting light towards us. Well, it's going to take some time to travel and get to the Earth, that light wave is. In the meantime, space is going to be expanding. And so that's why we see things redshifted. That expansion of space causes things to be redshifted. So while that thing may travel to Earth and it's going to take some amount of time, the place that emitted it is going to be expanding or moving away from us during that time. So the most distant thing that we can see is the cosmic microwave background radiation, which was emitted about 400,000 years after the Big Bang, or the earliest measurable part of the universe, if you will. That region that emitted that that's what's out at that distance of 50 billion light years. So while it's traveling, the space between us is getting larger at the same time.
Got it. So it's like the fabric, or it's like the tank of water that it's swimming through is getting progressively bigger.
Right. Yes. Yeah. And the hard part about that is that we can talk about the universe being 14 billion years old. We can talk about seeing something here, but the light that we saw was emitted many years ago. And so you got to account for the dynamics in between.
Cool. And in the book you mentioned, and you kind of alluded to here, different levels of multiverse. So like level 1 being the least exotic and going up, I think you said level 4. So level 1, if I remember correctly, is kind of what you said, where it's the same, physics are the same, it's just more universe.
Yeah.
Basically, like if you just got in a rocket ship and somehow could go faster than light, you could get to the edge. You just keep going, right? And there'd just be more.
And it looks largely like the stuff we see. Statistically speaking, it would be, you'd look up at the night sky, and except for the fact you wouldn't recognize constellations, it would basically just look the same. So,
and level 2 was more of like the multiversal foam, where you have different regions of different universes would have different physics, and they might look very different than what we experience. Is that right?
Yeah, and I want to be careful how we say that, because I don't know that they have different physics. Because when there's this terminology that at some point we'll probably get into discussing today, where there's this theory of everything that we think is out there, which that's the physics that describes everything. But as that may describe everything, but it's in the very high energy state, and as things cool, the low energy forms will look different. So when it cools, you get a certain speed of light or a certain strength of the gravitational force, those sorts of things. In these other realms, the low energy physics can look different, but presumably, or the idea is that it would all be described by that theory of everything.
So underlying all of it, there'd be some kind of like fundamental physics that is manifested differently in these different regions.
Right. Yeah. And kind of a way to think about that is, imagine a pencil balanced on its tip. in that region, it's like there's a great deal of symmetry. It explains a lot. When it falls down, it falls in a certain location, but there's nothing fundamentally different about it falling in the 180 degrees. It just looks different because it's in a lower energy state.
Got it. That makes sense. And then beyond that, we get into quantum mechanics, which we might get into, which I think is super interesting. But I think most when people are talking about the multiverse, they're talking about those two levels, I think, usually.
Yeah, because those are the ones where I think we have the potential of establishing that they exist. I don't know that we can ever measure them, but I do think there's some scientific questions we can ask. Although even within the quantum mechanics one, figuring out if we were to establish which interpretation of quantum mechanics is correct, that might weigh in on the validity of the quantum mechanical multiverse.
Right. I'm restraining myself from going into that.
Okay, all right.
One. I often hear when I'm talking to my friends and particularly Christians, not necessarily them, that they kind of have this idea of the multiverse as just something scientists sat around in a smoke-filled room and just made up because it sounded cool. The bastion of scientific research known as Answers in Genesis calls it a rescue device for the Big Bang cosmology. So what is it that convinces some scientists, at least, that we might be living in a multiverse of some sort?
Well, so I can tell you what convinces me that that's at least a possibility. I mean, I think I do not doubt that there are some scientists out there that say, oh, hey, the multiverse might solve these problems with theology. But I think in general, a lot of what led to the acceptance of the multiverse is, hey, there's a scientific basis for this. And then what people do with it is a whole different question. But where I thought, hey, the multiverse might actually exist was when I started thinking about what happens during inflation and how does inflation work. And just to give a little bit of the scientific background for that, as people were studying the universe, what they noticed was that the cosmic microwave background radiation was the same in every direction. And you're going back to your question of how can something be 50 billion light years away? Well, there's a problem that arises in that because that's the most distant thing we can see. Mm-hmm. So light has been traveling from, a region that's now 50 billion light years away. It's just now getting to Earth and we measure its temperature. Well, we look in the diametrically opposite direction and the same thing has been happening. Well, those two regions
they can't talk to each other.
They can't talk to each other. So why do they have the same temperature? Well, part of how inflation solves that or explains that phenomena is that they were actually in the same region and could talk to one another. And then this epoch of inflation actually drove them farther apart so that now they couldn't talk, or given the normal expansion, they could never talk to each other. But inflation meant that at some point in time, they were in contact with one another. So that was a cool thing in favor of inflation. It explained why the cosmic microwave background radiation could be the same to 1 part in 100,000 in every direction. There's another problem that inflation solved was when we look at our universe, it has very close to a flat geometry. And what I mean by flat is not piece of paper. It's how do light rays behave in the universe. And the best I can explain that is, if you say you can't talk about it in 3D because that's just hard. But if you go down to 2D, you can have three different classes of geometries. You could have something like the surface of a ball, where if you take parallel lines on the surface of a ball, eventually they converge with one another, they cross. Think of like the lines of longitude on the Earth. At the equator, they're all parallel. They all converge to the pole. That's what happened in a closed geometry, no matter how you slice it. In an open geometry, those parallel lines diverge. They get further apart. And in a closed geometry, which is kind of like a piece of paper, those parallel lines...
Flat, sorry.
Yeah, sorry, flat geometry. Yeah, thanks. In a flat geometry, the parallel lines always stay the same distance apart. And it wasn't, oddly enough, when I recognized that, I'm like, oh, that's what that odd statement was back in geometry class when I was in high school. They said, oh, yeah, parallel lines always stay the same distance apart in a Euclidean geometry. Well, Euclidean geometry is another way of saying flat geometry. And so, if things are flat, parallel lines always stay the same distance apart. And so when we look at our universe, we measure it relatively close to flat. And this was even 30, 40 years ago when we couldn't really make the measurements. It's still within a factor of 10 of flat. But the problem is flat is unstable. Over time, the universe, if it's a little bit deviates from flat, it will either go to closed or it will go to open. It's, again, going back to balancing a pencil on its point. It may stay there, but the moment it moves away very rapidly. So flat is unstable, yet lo and behold, we measure our universe very close to flat. Well, inflation explains why that would be, because inflation takes whatever the geometry was, whether it was closed, whether it was open, whether it was flat, and it just takes that small region, expands it very large. Imagine taking a golf ball, you can see the curvature, but you can only see something about the size of a quarter. Now expand it to the size of the Earth. You still only see the size of the quarter, but it looks flat within that size of the quarter. That's true. So inflation explains why is the cosmic microwave background radiation the same. It explains why the universe looks flat, and it also explains why there are no magnetic monopoles. And believe it or not, that's actually solving that problem was what actually led to the invention of inflation. And so inflation solves all that, but it does so by taking a very small region, making it very large, which means that there is stuff beyond beyond the limits of what we can see. And so this idea, what I'll call a level 1 multiverse, and I just say right up front that I'm shamelessly taking that terminology from Max Tegmark. He developed it and I liked it. I say, hey, this is great. So I will advance the terminology and give him credit. But that level 1 multiverse, if inflation happened, we live in a level 1 multiverse. There's stuff beyond that we can't see. There's stuff beyond what we can see. And if inflation happened, it tells us that it's out there.
Okay, so if there was inflation, then the question of whether there's a multiverse of some sort is settled, and the answer is yes.
Yes. That's my understanding. I mean, I'm willing to be convinced that that's not the case, but I don't think you're going to be able to do it. So
fair enough. So how big then would big be? Like, how much would be outside of this 50 billion light year cone that we're in?
Well, so we can put a limit on how large it must be, and we know it's got to be at least 50 billion light years across.
Yeah.
How big? There is no way to put a number on that. Even some kind of small estimates say in order to count for some of what we measure in our universe, it needs to be at least 1,000 times larger. But most cosmologists that I hear writing and talking about this would argue that space is spatially infinite.
Oh, wow. Okay. So I think now we can segue into some of the fine tuning things, because often that's in Christian circles, the multiverse is couched in fine tuning terms. And so for anyone who somehow stumbled on this episode and has never heard of the fine tuning problem, basically the idea, and correct me if I oversimplify it, the idea is that we find ourselves in a universe that seems to some extent, in some way, fine-tuned for life, for us, for complex observers. And so the natural question is, well, how come? How come things are in such a way that we're here? And so that's the fine-tuning problem. And of course, the Christian answer is, well, it's that way because God made it that way. And, and he wanted us around for whatever reason. So it seems like the level 1 multiverse could go part of the way to answering it when it comes to, like, you call it environmental fine tuning. So like the Earth and how well adapted that is to spawning life, right? If we had a spatially infinite multiverse, I mean, that would mean that there'd be an infinite number of life supporting planets, right?
So in principle, yes. I mean, there is an assumption smuggled into that statement that I think is important to talk about. But yeah, your basic idea is correct. The assumption is that things largely look the same beyond what we can see compared to what we can see. And in that sense, if the Earth needs to be a certain size, if you got to have a certain kind of star, if the distance needs to be the same amount, you got to have. Those are all things that we look and see. Stars can be different. We can look, planets can be different size. They can be different. So anything like that that's kind of environmental where it could change and we see that it can change, then in principle, yes, if you spread that out enough, or if space is just large enough, with every probability or fine tuning, and again, I think how we say that is important, but generally fine tuning is couched in some sort of probability or ratio. Mm-hmm. Well, when you're talking about probabilities and ratios, you have to talk about the ratio, but you also have to talk about the sample size.
Right.
The illustration I always give, if you're sitting down and playing poker and I get dealt ace, king, queen, jack, 10 of spades, I'm saying, wow, that's improbable. That's unlikely. It's like somebody designed me to get this. But if I now go and say, there are a billion people playing this game, those are going to happen. In fact, there better be more than me that has them, because that's a 1 in 2.5 million chance of getting that. So if we got 10 billion hands, there ought to be a lot of them. And so effectively, the level 1 multiverse provides this really large sample size that overwhelms whatever probability or ratio you're talking about.
Do you think that it needs to be spatially infinite to do that? Obviously, an infinite sample size would take care of any ratio problem you have, so we're not worried about that. But if the multiverse, if this level 1 multiverse is truly 1,000 times larger than our observable universe, is that, in your opinion, big enough to take care of environmental fine tuning? It seems like, there's a lot of planets in just our observable universe, and if the universe as a whole is 1,000 times larger than that, just those numbers get truly. I literally can't contain that kind of number in my brain.
Well, no, you're right. They do get larger. The question is, how tuned are they? If I say, I've got something between 1 and 100 and I can only measure 3, well, if it could be integers between there and I can measure 3, well, I can say, all right, well, that's, this is tuned to 1 part, or 3 parts in 100. Well, if I now say, all right, I know the sample size is 8 times larger, I'm now 20, or I've got 24 samples out there, but that's still 24 out of 100. That's 1 1/4. So it kind of depends on how precise the particular factor or parameter is and what the size is. And so obviously infinite would overwhelm any probability or any ratio. But the question, or anything smaller than that, or anything finite, now you have to ask the question, how tuned is the parameter and is the sample size large enough? And those are not quantities that everybody agrees on. And so, I can find people who say, well, there's only 2 or 3 parameters. I can say there are people who say there's 100 parameters. And, so that's a subject of scientific discussion there.
Gotcha. So, NASA has been looking for exoplanets, and they say about half of, I saw on their website, about half of sun-like stars have a rocky world is their estimation.
I've heard a little closer. I've heard it down about 20%, but it's not really significantly different. But
I think that the difference comes in sun-like, and if you confine it to that, yeah, because if you broaden it to less sun-like stars, then that changes it.
Fair point.
So I guess I'm asking, how fine-tuned do you think it is? Like, in the book, the words you used were the probabilities stack up against finding even one planet that would fit the bill. Do you think that the conditions needed for life are really that fine-tuned that we wouldn't expect to find more than one?
So, I've thought a lot about how I would phrase that. That book may be long enough ago that was before I thought carefully about how to talk about that.
It was 2008, to be fair, so it is a while.
It's a fair bit ago. Yeah, I'll give you that.
Yeah.
And again, the question is, we're dealing with areas where we don't have all the scientific knowledge, and so I kind of see there's 2 classes of models of how people look at that. One is which I kind of term a minimalist model, where get liquid water and life's going to happen. So in that sense, you got to have the right distance from the star. There's probably a few atmospheric constraints, but even within our solar system, there's lots of places where liquid water has existed. Early in Mars history, it almost certainly had liquid water. There may be liquid water on Europa today, buried under ice. And so in that minimalist model, there's lots of different ways to get water. And so where you're going to have water, you're going to have life arise, at least in some reasonable fractions of those. And then there's kind of what maximalist isn't the right way to say it. I never have come up with a good word for it, but a more strict set of conditions where, when I look at what's gone on Earth, early Earth was very different than the Earth of today. The Earth's oceans were filled with water. There was virtually no continents or landmass to speak of. Very primitive to no life, no oxygen in the atmosphere. The sun was 30 to 40% dimmer than it is today. In the last 4 to 4.5 billion years, there have been incredible astronomical changes, geological changes, atmospheric changes, biological changes. And yet in the midst of all of those changes that could very easily have just decimated Earth's capacity to host life, Earth's temperature, to the best we can measure it, has stayed within about a 20 degrees Celsius window, right around where liquid water can exist. And so that to me strikes of an orchestration where, when you've got this great oxygenation event, which is going to put oxygen in the atmosphere, remove all the methane, create carbon dioxide and water, that's going to drive the planet into a global ice age because you've now removed a very potent greenhouse gas from the atmosphere. But that's also right around the time where a significant amount of tectonic activity is happening, which puts greenhouse gas, which counteracts that. And so all that to say is that, that there's kind of this minimalist model where we get water, we're going to have life. And there's kind of a maximalist model where there's more than we even know to talk about, but yet we see this extreme changes going on, and yet the conditions that life requires have been maintained. And what I would say, the way I would characterize that is, apart from God's work, I wouldn't expect to see that anywhere in the universe.
I don't know, 10 to the 25 seems like a really big sample size.
It is, but we're talking about some pretty extreme things. It's the range of conditions in the universe that are inhospitable to life are incredibly large compared to the ones that we know are hospitable to life.
That's true. Most of the universe wouldn't be conducive to human life if you were just thrown into a random spot of the universe. The odds are not good. So,
right.
That's true. Okay, so the environmental conditions, maybe it really comes down to how tuned the Earth is, how special the Earth is. Mm-hmm. And that's something we might actually be able to answer, perhaps not in my lifetime, but maybe in my children's lifetime. Maybe they'll get to know. So maybe that answer will be settled. Moving on to the other fine-tuning problem, which I think you called, now I can't remember what you called it, the universal fine-tuning problem when it comes to the fundamental constant. Fundamental, there, thank you. I swear I read the book.
Well, that tells you that because you knew I had divided it into 2 classes, so you had to read it that far.
Well, you did that in the first few pages, so I wouldn't have had to read it. But in any case,
you kind of.
In any case, when it comes to fundamental fine tuning, that one seems a lot trickier because while we have at least a sample size of one, and we can look at other planets, if there is fine tuning when it comes to the physical constants, it seems like we're pretty much stuck with the physical constants we have. So you mentioned how the laws of physics could manifest in a range of possibilities, right? Mm-hmm. And so the idea is that there's some kind of range that would permit life, however broad or narrow that range is. How would we go about assessing that kind of probability? Because we've got this sample size of 1, right? And we don't know how the laws of physics came about. So, when we say things like, it's improbable we get this constants like this with this vast range. Well, how do we know that there's actually this vast range?
No, that's you have identified a extremely difficult, if not unsolvable, problem in physics. Is that so we say, okay, the speed of light is 3.3 times 10 to the 8 meters per second. Could it be different? Well, we could in principle envision it being different. I mean, I can do calculations where the speed of light is 10 times larger or 20% smaller. But what we don't know is, can it actually have a different value? And that is going to be model dependent. There are certain, in this idea that the laws of physics are unified, and as the universe cools down, you get symmetry breaking and you get these certain results in that model, then yes, certain parameters of the universe, like the speed of light or the gravitational constant or the electromagnetic constant, could presumably take different values. But the challenge in this universe is we have no way to measure that, or we have no way of, it's a reasonable idea, but I don't know how you get experimental evidence that validates that it's a correct idea.
Right. So you said it's model dependent, the answer to that question. So really it seems like the answer is we don't know how likely our constants are. Okay, that's fair. Can you give us a feel, at least in your opinion, like what kind of level of tuning are we talking about here, potentially?
With the caveat that we've already discussed that, like with the planets, I can talk about, well, there's this many planets and there's only this many have. And so I could put numbers to that. I really don't know what the speed of light could vary. And that's one of the challenges when you're talking about the multiverse, and does it address this, is that we cannot measure, let's just say that, yes, the speed of light can vary, plus or minus a factor of 10 with some sort of resolution to it. Well, given enough other universes out there, presumably you could explain just by statistical reasoning why our universe has this value. Okay, let's just say that. The challenge is there's no way of determining whether that's correct, or we go out and every one of those multiverses has the identical value for the speed of light. Both of those are equally valid logically, according to what we know. But to my knowledge, there's no way to experiment and say, well, it could be different. With one exception, it is possible, and there are people who are doing these sorts of experiments, that when you look over the distant reaches of space, it is possible that the constants could change within our observable universe. And there are people who have looked for, you can look at distant quasars and it gives you a measure of the fine structure constant, which is a mixture of the speed of light and Planck's constant. And as a physicist, I got to know this. It's either the mass of the electron or the charge of the electron. I'm pretty sure it's the charge.
Tell me which one it was, and we'll edit out the other one.
I'm going to go with charge, and I'll claim I just need to look at it in a book if somebody gets too gripey at me. But so what people are looking for is, we can measure that value here in the lab, and with our telescopes, we can measure what it is out in these distant quasars, and we can ask the question, is there any evidence that it's changed? And granted, the statistics and are hard to do, and our uncertainties are hard to quantify, but there's some marginal evidence that maybe these things change over the expansion of the universe by 1 part in maybe 100,000. So that would give us a way of measuring, maybe these quote unquote fundamental constants could take on different values. That's it. That's one that won't take your lifetime and my lifetime to assess. I think somewhere within the next maybe decade or two, we might be able to get a better handle on that way of looking at it.
So then at least we would know the changing of the constants is a thing that can happen potentially.
Yeah, that's what that would demonstrate, yes.
Yeah, that's both neat and terrifying. I remember in my modern physics class, which is, I think, a sophomore level class or something, as far as I went, but I went in as an engineer, and there's, physics, and there's constants and things are preserved. And my professor's like, and, definitely on short time scales, entropy isn't preserved. And I was like, okay, I mean, it's stochastic anyway. He's like, and also angular momentum. I was like, what did you just say? So just the idea that the fine structure constant might be unstable is unsettling. But anyway.
It is at some level, and what's the fascinating part about that is that to the extent that might be true, that actually takes those fundamental fine-tuning and make them environmental. because in principle, if I were to move far enough away to get into just this level 1 multiverse, if I were to move far enough away, I might be in a region where those fundamental things could be different. So this is the sort of dynamics of, I put it all in the terms of speculative cosmology, not as in a pejorative sense, but it's like, well, it might be, and it's reasonable, but we don't have the experimental data to weigh in one way or the other on it.
So is there any hope for confirmation of a level 2 multiverse? I know that one of the reasons that people think there might be a level 2 multiverse is that certain interpretations of string theory would lead to different laws of physics, right? And so if string theory is correct, then a level 2 multiverse might kind of fall out of that. I know you're not a string theorist, right? But is there any hope for confirming that in anybody's lifetime?
Maybe or maybe not. So I made a statement not too long ago or earlier in the show where if inflation happened, we live in a level 1 multiverse.
Right.
Well, physicists aren't content with just saying, "Oh, yes, inflation happened." They want to say, "Well, what caused inflation to happen? How do we explain it?" And that's an entirely fun discussion to have because there's these potentials and things are rolling from the ground state or from this excited state down to ground state, and you get inflation and decaying of false vacuum and all sorts of fun terminology to play around with. But the where that comes into where inflation can now explain our universe is that there was always this problem with inflation, is that if our universe started and in this early epoch there was this phase change that caused inflation to happen and then inflation stopped, one of the problems with that is that it always produced a clumpy universe. And not clumpy as in stars, planets, and galaxies, but clumpy as in the cosmic microwave background radiation would have all sorts of different temperatures no matter what direction you looked. Or every direction you looked would have a different temperature. It was called the graceful exit problem. Well, in the late 70s, early 80s, Alan Guth and others figured out how to solve this by saying, you know what, if you've got this region of stuff, we'll call it a false vacuum, that just very rapidly expands, where it decays to the ground state, now you've got a bubble that's formed in there, and that bubble will contain our universe. And so now you've got inflation and our universe, and it explains our universe in a way that matches the observations. And so in this version of inflation where you've got something that just rapidly expands and it decays, you watch a pot boil, it's not just going to have one boil, it's going to have a bunch of bubbles. And so similarly, this false vacuum is going to decay in a whole bunch of places, presumably create a whole bunch of different other universes. And you can do that in multiple ways. But all of the mechanisms that drive that, well, virtually all the mechanisms, or all that we've investigated, produce this level 2 multiverse. Okay. So going back to your question, could we ever confirm that? Well, if inflation happened, we live in a level 1 multiverse. If any of our mechanisms for explaining inflation are correct, we live in a level 2 multiverse. So if we could in some way say, oh, this kind of inflation produces this signature in our universe, then we could say, that counts as evidence for this mechanism of inflation. And the consequence of this mechanism is there's a level 2 multiverse. So that's the sort of confirmation we could potentially get.
Well, that's a lot better than nothing.
It is, and it makes it a fun scientific arena to investigate and has a lot of just cool philosophical implications as well.
Well, that's a great segue. So we've talked about the physics. What does this mean when it comes to talking about God? So obviously, if God's infinitely powerful, he's perfectly capable of making as many universes as he'd like. But do you think that has any kind of philosophical implication on Christianity specifically, or just God's claims in general?
Well, that was originally my question when I started investigating this, because a lot of the things that I first heard when I first heard about the multiverse, and people were talking about it, and the sentiment has been expressed for a long time since. It's either God or the multiverse. And so, to me, any evidence for the multiverse, well, that counts against God. And so that was kind of the approach I took. And then as I started reading and investigating, I'm like, if inflation happened, we live in a level 1 multiverse. That's not a scientifically controversial idea. Maybe the multiverse is going to turn out to be right. And so that got me asking the question, okay, exactly what you asked. How does that impact Christianity? And what I've recognized is this. the Bible actually talks about things that we could call a multiverse. There's this creation. Bible talks about the angelic or the spiritual realm, which in some sense is another universe, if you will. The Bible talks about how there's going to be a future where this universe is accomplished its purpose, it's going to be destroyed, and God will create a new creation that, given the brief description we have, certainly looks like the way physics plays out is very different. And so the idea of a multiverse is not unbiblical. I mean, the Bible describes multiple realms that God has created. And so there's nothing inherently about the multiverse that is unbiblical. I do think there are certain ways of looking at the multiverse, or certain extrapolations of how you use the multiverse to explain what we see, that do cause problems. One of those being that if everything is purely physical, this is the one that I think resonates the biggest to me, is that if everything is purely physical, then Jeff Zweerink is just a proper assemblage of atoms with the right velocities and momentums in the right locations. Well, level 1 multiverse says that configuration of atoms is going to happen somewhere else. And so Jeff Zweerink not only exists here on Earth, but he exists somewhere else. He could exist out in the vacuum of space multiple times. And if the universe is infinite, spatially infinite, that level 1 multiverse, not only is there not only just one Jeff Zweerink, there's an infinite number of them. And so these are kind of some of the theological places where I don't know that it's such a big deal with Jeff Zweerink, but Jesus Christ also had a physical body. And so is Jesus Christ getting replicated throughout These are the sorts of theological questions that I find interesting.
I wonder, did every Jesus Christ get crucified? Maybe in some other places, he was sacrificed in some other way,
Exactly. These are the sorts of questions that arise. But again, notice that that's not, the multiverse says that. That's the multiverse and this additional stipulation that human life specifically is solely physical. And so those are some of the interesting philosophical and theological questions that I find arise out of this discussion.
So if it turns out that we do live in a level 2 multiverse, it seems like that at least has a potential to address the fine-tuning problem from just kind of a selection effect. We find ourselves in the version of the universe that we could find ourselves in. That's not surprising. But it doesn't seem like that would, like you said, necessarily say, well, therefore God doesn't exist, because it could, I think, at most take out a potential argument for God's existence, but it's not certainly the only argument for God's existence. Yeah.
Right. And what you're describing is kind of my original strugglings with this, because when I first recognized, hey, the multiverse might exist, well, I see the implication for the these fine-tuning type arguments, or I'll call them probability arguments, because there's other ways of talking about fine-tuning, but the probability arguments for the fine-tuning, because large sample size overwhelms however small probabilities you have. And there was this other implication that was unknown, what the consequence of this was going to be, is that once inflation starts, it goes on forever. And it's just this bizarre phenomena that whatever is expanding, it may decay, but in the time, whatever decays in that time, there has been more stuff expanded. So the total amount of expanding stuff is always constant. And so once inflation starts, it goes on forever. The question that naturally arose from that is, might it have always been going on forever? So this inflationary multiverse, not only might it have solved the probability fine-tuning arguments, it might also solve whether there's a beginning or not. It might have gotten rid of the beginning. And so there was a better part of a year where I'm sitting around investigating this, where, like I said, it's not that would disprove Christianity. It just says it may remove arguments that I'm using for Christianity.
Yeah, I think that's something, if nobody takes anything else away from this on both sides, because I hear it from my fellow atheists, and I hear it from my Christian friends too, where they cast it just like you said, where, well, God doesn't exist because the multiverse, and that doesn't necessarily follow. I hear that from my atheist friends. And then you've got people on the other side who are just like, who I think are motivated sometimes in their objections, not because of the scientific evidence, but because they feel threatened. I don't want to psychoanalyze, but I know that can be a thing, and I don't think that's necessary. Whatever the truth is, that's what the truth is, right? And
Mhm.
if God exists, then the evidence we see should support that. So we shouldn't have any, no worries. So,
Amen.
yeah, sorry, I'd get off my soapbox there. Okay. Well, I'm going to indulge myself now because there's another level of multiverse that you bring up very briefly in the book. You barely mention it, just enough time to put it aside, but I'm going to step into that breach anyway. The third one has to do with quantum mechanics, and specifically the Everettian or many worlds interpretation of quantum mechanics. And basically, my understanding of that is that, well, quantum mechanics has, as we observe it now, a base level of indeterminacy. We have a wave function. You're in a superposition of A and B. Somebody observes it. There's some kind of observation, and now the wave function collapses into A or B indeterminately with some kind of probability.
Mm-hmm.
And why does it do that is the question that not many people seem to ask, but it is a question. So if one of the interpretations of quantum mechanics is right, the Everettian view, the wave function doesn't collapse. They both exist. They just split off into different universes, right? Kind of. And so winding it from the Big Bang to the future, you'd have this branching tapestry of all possibilities. So first, how crazy does that sound to you? I guess.
Well, there's part of it that sounds really crazy, but I do have to wrestle with this fact that one of the ways that you can go about calculating a quantum event, whether it's electron scattering, whatever you're talking about, is you draw out all the Feynman diagrams and you just calculate all the probabilities of all of them. And what's obscured in that language of that is that you're assuming that the electron actually takes every possible path in what it goes. So you're saying this has a contribution, this has a contribution, this has a contribution. And so you're saying the electron did all of this, and we sum it up and we get the right answer. And what's amazing is you get the right answer when you do that. You also get the right answer when you assume there's a wave function and it collapses into one state or the other. And what's interesting about all that is, so I've got to wrestle with the efficacy of calculating based on this idea that all of these worlds exist. But there's also this recognition that, at least 5 years ago was the last time I checked. If you go look on the Wikipedia page and you say interpretations of quantum mechanics, you'll find this chart that lists 17, 18 different interpretations of quantum mechanics. Mm-hmm. And what's unusual about that is nobody goes out there and says, here's my interpretation of general relativity. The mechanism of general relativity drives the equations. We don't know what's going on with quantum mechanics. And so you could have the wave function collapses. You could have it takes every possible path. You could take all those worlds and you're just traversing a trajectory through all of those worlds. And there's other ones, there's decoherence and all different ways of looking at this, which to me basically just says, okay, we are very effective at calculating the probabilities of quantum mechanical events, but we really don't have a good understanding of the actual reality behind it. And that gives me great pause to say, well, the Everett's many worlds interpretation is correct, or Copenhagen's waveform collapse is the correct. We can calculate whatever we want, and maybe as we move into the future, we're going to be able to devise experiments that will differentiate them. But right now, there's a lot of different interpretations, and so you want to take an Everett. I'm not even sure how to say that as an adjective, but take Everett's. Yeah, okay, great. Everett's interpretation. Great, go do that. If you want to claim now that this is the way reality works, now we've got a whole different level of discussion, which I don't think you can validate by what we know.
Since I have a physicist in front of me, and I don't often have one sitting in front of me, is there any work being done to try to find the answer to this question? It seems like a lot of physicists have the idea, at least from my outside looking in perspective, of shut up and calculate. We've got great equations that give us good results, and while I can empathize with that view as an engineer, shut up and calculate is everything I do. Is that an active field of research that people are actually trying to figure out?
Oh, yes, they are. I mean, I'm not. I have not done a lot of work reading in that, but I do know there are people trying to figure out and the way the model out there that I've heard that seems, or at least one of the more popular models, is this idea of decoherence. That when you make a measurement, instead of A and B, so there's up and down, and when you make a measurement, it's down, so B just disappears. What happens is there's this decoherence where this reality becomes what is the one you interact with, and there's a question of what is actually going on over there with the other. But so there is a very active area of research and trying to devise experiments where these interpretations may have had a lot of common ground, but on this experiment they're going to predict different things, and it's a challenging area. I don't know that there's any decisive work in that area, but I do know it's a very active area of research.
So this type of multiverse doesn't seem to bear on the fine-tuning problem as directly as the other two do, because for obvious reasons. Because the same physics would predict, if the Everettian view or the decoherence view or whatever view it is, that'd be the same on the physics, right? But let's say, just for the sake of discussion, let's say that Everett is right, and it is the many worlds interpretation. That's the kind of world we live in. It seems like that might have some potential bearing on theological discussions, like what you talked about with the infinite multiverse. What about Jesus and having, he if he had a physical body, were there tens of thousands of Jesuses, that's right. That could be tricky. If in the Everettian view, it's basically any possible quantum event that could happen did in fact happen, then it seems like there'd be. It seems like you'd have not necessarily infinite, but a large, arbitrarily large number of events. A version of me where I'm me sitting here and I'm an atheist, and a version of me where I didn't deconvert, I'm still a Christian, and maybe one where my grandfather never left India, so I'm a Muslim. So it seems like that could potentially have some theological implications, right? Because then there's no unique me anymore, at least in some sense there's not.
Right. I think it does have profound theological implications, and not just for Christian theology. I think for what it says about how the world is, because essentially, I mean, I may be wrong, but as I'm sitting here thinking, or have thought about what does that sort of explanation do? So essentially, the reason why things are the way they are is there's this large statistical population, and we just happen to be one of those populations. That seems a very deterministic way of talking about things. So, here we are having a discussion, and at some level, you would say you made a choice that Christianity is not true, and I've made a choice that says Christianity is true. We actually think we made a choice, but if that way of looking at it is correct, we're just in the distribution of things where that happened. So at some level, it seems like at a very fundamental level, we're just pawns in the outworking of the laws of physics, which may be true, but that is a theologically disturbing conclusion to come to, regardless of whether you think God exists or not.
Yeah, I mean, it's certainly, I tend to lean towards the idea that the universe is deterministic anyway, just because it suits my sensibilities, but I'm not married to the idea. I mean, it seems likely, at least at a base level, there's some indeterminism unless certain branches of quantum mechanics are right. So that doesn't bother me too much, but it certainly would be an issue with, like you said, questions of choice, or it seems like it would just completely throw away free will, because you just, it's the crapshoot as to which branch you in big air quotes, you happen, for people who aren't on YouTube, in big air quotes, which branch you happen to be on. It's kind of, in one branch, Hitler got into art school and everything's fine.
Well, and beyond that, I do worry what that will do for the implications it has for science. And that may sound like an odd statement, but just to give a little illustration. When I was first in college, you take an intro physics class, and there's a lab you take. And one of the labs, you have these air tracks, and the carts move along, and you can put dots on pieces of paper. And this is back where you actually had to have rulers and none of the smart technology that exists today. But one of our tracks, there was just this dot that was just way off from what we expected. And so one of the questions in there was explain, what are sources of error? Explain why it is the way it is. And so my lab partner said, well, that was a passing black hole. Thought, okay, that's kind of funny. So we put that on there. Our professor wasn't particularly amused with that. But that's actually a pretty reasonable explanation. It is an explanation for why that point would have been different. Now, if the multiverse is true, how do I determine that that's not the correct answer? Well, almost everything we do in science everything we do in science is there are a myriad of explanations. These are the most likely. If the multiverse exists, we're no longer assuming that what we found corresponds to reality. We're just finding the most likely explanation. But in the multiverse, there was somewhere where a black hole passed by that and caused the dot to be in the wrong place. How do I know that? We know that science works. We know that the formalism and the structure and the thought process and the system we've built works. But it's predicated on basically being able to ignore all the highly improbable events. Well, now we're using the multiverse to solve a highly improbable event. Why do we do it there but not everywhere else? And this is, I don't know whether that's an unsolvable problem or not, but it does seem part and parcel with using the multiverse to solve rare event problems, because now you have to deal with every rare event. And that becomes problematic because there are other very rare ways of getting life in the universe besides the history of life that we see here on Earth. And now you have to wrestle with those sorts of questions as well.
It seems like you could just do the same thing that we've always done and just kind of ignore the very rare events. Like if you just looked at the ensemble of the multiverse, and if you have an event that's however many times as likely as another event, absent any evidence to the contrary, we're probably in the more likely one, even if there are, a multitude of different options. If you were just throwing a dart at the wall, there's still just a bigger target for the more likely event. I mean, I'm not sure why the multiverse would necessarily throw that model away.
So, my suspicion is that there's an aspect to where I know I have been inculcated in the idea that we're finding the most likely event is the one that corresponds to the truth. Occam's razor, as it plays out in science, is the simplest explanation that accounts for all the data is likely to be true. Mm-hmm. So there's this philosophical idea that we brought into doing science, but it's predicated on the idea that we're actually trying to figure out what actually happened. And if you now remove the basis for that, which the multiverse would do, you're correct that there's statistically certainly more likely ones than others. But if you play with that way of looking at things long enough, what prevents you from getting to the place where it's like, well, this is a fun game to figure out what's the most likely, but it has no correspondence to what's actually going on. Why do I keep doing this?
It would certainly take away the possibility of being able to say definitively that X happened. Mm-hmm. The best I think you could say is, well, X is the likeliest explanation, and that just has to be good enough to deal with it. I guess the answer to why we keep doing it is because it produces good results. I mean, as long as it continues to make accurate predictions, I guess we're still good, at least to my mind. It could. I think that's the kind of problem that philosophers of science would wrestle with and get very worked up about. And I'm not certain that Joe, engineer would get very worked up about it, if
No, and that's a fair point. And I, like I said, I don't think if we were to immediately say, oh, yeah, the multiverse is the good explanation for everything, my guess is that science would continue on for another 20, 30, 40 years and largely be unaffected. But at some point, that next generation is going to be inculcated in a different way of looking at the world than I was. Mm-hmm. And I wonder what that will produce.
Yeah. Interesting time. Well, we've been going for about an hour, and we've been going for 56 and a half minutes, give or take some seconds here and there. So I want to wrap up a bit. Is there anything going on, any books you're writing that you want to talk about real quick? Because I only have a sample size of 2. I've only read 2 of them, but 2 are very good. So.
Well, I'm encouraged to hear that. Thank you. A lot of what I've been thinking about lately is just artificial intelligence, the metaverse, the kind of that foray that we're making as his humanity out into the digital world, and AI, like the multiverse. There's different kinds of AI, and the AI that I think of is the R2D2s, the sentient silicone creatures. That AI is here, but it's not that AI. And so I think that's a very interesting discussion. And just kind of been thinking about how to interact with that. And the argument I'm trying to make in there, as I've thought about it, is that AI is a pretty powerful tool. The question, given the power of that tool, I think the worldview we adopt is going to go a long way towards whether this tool is used to benefit humanity or to the detriment of humanity. And I'm going to trying to make an argument that I think Christianity is the worldview that allows us to bring the good while minimizing the harm. And so that's kind of what I've been working on.
Okay, that's interesting. I think the field of AI research is super fascinating, possibly troubling. If you read about strong AI and the possibility of a singularity, where basically at that point it'll be down to how well the guy in the basement programmed it, to whether we have a benevolent overlord or humanity goes extinct. But yeah, that's super interesting. So I'll be on the lookout for that. And I wanted to thank you again for taking time out of your day to come talk to us on Reasons to Doubt. It's just me today. I guess I probably should have mentioned this before. My host, Jared, is feeling sick, so he wasn't able to come. For anybody who's wondering why it was just me, he didn't die or anything. But thanks a ton for coming. I super enjoyed it. And I hope that we'll be able to talk again, because this was like the highlight of my week right here.
Well, I appreciate the time to be on here. Just fascinating. I love talking about the multiverse, but just really enjoy it. I think there's just a lot of cool, fun conversations that grow, and some really good questions. So thanks for having me on.
Thanks. So make sure you check English. Make sure to check out Jeff's stuff. He's with Reasons to Believe, like we talked about, and be on the lookout for our new stuff on the horizon. And while you're doing that, remember, you always have reasons to doubt and believe, as it turns out.